All right, let's dive in. You've probably seen chemistry happening all around you, maybe without even labeling it that way.
Oh, yeah. Like what?
Well, stirring sugar into your coffee, mixing up some squash or juice with water,
Yeah.
even just opening a fizzy drink and seeing the bubbles.
Ah, right. Dissolving things.
Exactly. It's all about things dissolving.
Yeah.
And if you were with us last time, you'll remember we talked about the states of matter, solid, liquid, gas.
Mm-hmm. The basics,
That understanding is kind of the perfect launch pad for what we're getting into today.
which is
Solutions.
right.
We're going to tackle this pile of material you sent over, really break it down and figure out what solutions are, how they form, and what makes them tick, especially thinking about how this works in a lab setting.
Good plan.
Yeah.
So, starting point.
Yeah.
What is a solution? The sources define it as a homogeneous mixture.
Homogeneous. Okay, keyword. What does that mean exactly?
It means it's completely uniform, the same all the way through. You can't see different bits, not like, say, mud and water.
Right, not like sand settling at the bottom.
Exactly. And it's made of typically two parts. There's the solute, that's the stuff you have less of,
Okay.
and the solvent, the stuff you have more of. And usually the solvent state, like liquid water, determines the state of the whole solution. Salt water is liquid.
Okay, got it. Homogeneous, solute, less, solvent, more. But how do we know if something will actually dissolve in something else? There's that classic phrase everyone learns.
You mean like dissolves like?
That's the one. It sounds so simple.
It is simple, but it's incredibly useful for predicting solubility. It's all about the molecules.
So what does like mean there at the molecular level?
It boils down to molecular structure, specifically polarity.
Hmm.
Whether the molecule has slightly positive and negative ends, like water does, that's polar.
Mm-hmm.
Or if the charge is spread out evenly, that's nonpolar. Like dissolves, like just means polar things tend to dissolve well in other polar things.
Like ethanol and water, both polar.
Exactly. They attract each other nicely. And nonpolar things dissolve well in other nonpolar things, like oil and grease mixing together.
But oil and water, no dice. Polar water, non-polar oil. Not like
Precisely. The attractions just aren't favorable, so understanding polarity is crucial if you need to dissolve something in the lab.
Okay, so that's if they dissolve. What about how? The sources mention it's a kind of step-by-step process.
It is, yeah. It's not just magic. There's energy involved.
Yeah.
Basically, you have to break the attractions within the solute and within the solvent first.
Okay, step 1, pull the solute particles apart. Takes energy.
Right. Expand the sauce. Step 2, make space in the solvent. Expand the solvent. Also takes energy.
And then
Step 3, let the separated solute and solvent particles mix. This step usually releases energy as new attractions form between them.
so there's an energy balance. It can release heat overall or take it in.
Absolutely. Exothermic or endothermic. And a key point here is if steps 1 and 2 require a massive amount of energy compared to what you get back in step 3.
Then it probably won't dissolve easily.
Exactly. Nature tends to avoid processes that require huge energy inputs without a good payoff. It links back to those intermolecular forces again.
The like dissolves like idea.
Right. The sources emphasize that a solution forms readily if the new attractions between solute and solvent are stronger, or at least comparable, to the old attractions within the pure solute and pure solvent.
Makes sense. The new situation has to be favorable enough.
Yeah.
Okay, so we know what they are, how they form. Let's get practical. In the lab, you don't just make any old solution, right? You need specific strengths.
You absolutely do. Concentration is critical. It's the way we say exactly how much solute is in a certain amount of solvent or solution. It's fundamental knowledge for any future chemist.
How do we think about that? The sources had a simple example.
Yeah, the teaspoon one. Like 1 teaspoon of sugar in 100 milliliters of water. That's a certain concentration.
Okay.
Now, if you put 2 teaspoons in 200 milliliters, you've doubled the sugar, but you also doubled the water. The ratio is the same.
So the concentration is identical?
Yeah.
Same sweetness, basically.
Right. But if you put those 2 teaspoons in the original 100 milli.
No, it's definitely more concentrated, stronger taste. It's about the ratio.
Exactly. Solute amount relative to the total. And because we need different ways to express this for different tasks, chemistry uses various concentration units. The sources list a bunch.
Yeah, I saw percentages.
Yeah.
Like weight, volume.
WW percent, those are common.
And then the ones based on moles, which seem really common in chem labs.
Definitely. Molarity is probably the big one. That's moles of solute per liter of the final solution. Symbol M, or molo.
Okay, molarity. What else?
There's molality little m, which is moles of solute per kilogram of the solvent. Slightly different.
Solvent mass, not solution volume.
Interesting. Then mole fraction ratio of moles of solute to total moles.
Mm-hmm.
And for really tiny amounts, you get parts per million, ppm, or even parts per billion, ppb.
Wow, lots of ways to say how much is in there.
Pretty much. Depends on what you need it for.
So let's say you're in the lab.
Hmm.
Task: make a solution of, I don't know, copper sulfate with a specific molarity starting from the solid powder. How do you do it accurately? The source has laid out steps.
Yes, a standard procedure. First, you calculate the mass of solid. You need like that 27.5 grams of QSO4 example.
And you need an accurate balance for that.
Precision is key, absolutely. Then you take that weighed solid, put it in a beaker, and add maybe about half the final volume of solvent you'll need.
Just enough to get it dissolved.
Usually, yeah. Swirl it, stir it, make sure it all dissolves. Get a clear solution.
Okay, solid's dissolved. Now what?
Now, carefully transfer that solution into a volumetric flask. Those are the flasks with the long, skinny necks and one calibration mark.
Ah, because they measure one specific volume very accurately.
Exactly. But you don't want to leave any solute behind in the beaker.
Right. So you rinse the beaker.
Multiple times. Small amounts of solvent, swirl it around, pour the rinsing into the volumetric flask, get every last bit.
Good tip.
Then you carefully add more solvent to the volumetric flask, bringing the liquid level up until the bottom of the meniscus just touches that calibration line on the neck.
So you hit that target volume precisely, like the 500 millioil in the example.
And boom, you have your solution with the desired concentration.
Okay, that's from a solid. What if you already have a concentrated solution, a stock solution, and you just need to make a weaker one? Dilution.
Dilution, yeah, super common. Step one is always a calculation. You need to figure out how much of that concentrated stock solution you need to start with.
And there's a formula for that.
The essential one, C1V1 equals C2V2.
C1V1 equals C2V2.
C1V1 equals C2V2. Initial concentration times initial volume equals final concentration times final volume.
Spot on. You know, C1, stock concentration, C, target concentration,
Yeah.
and V2, final volume you want.
Yeah.
So you solve for V1, the volume of stock solution you need to take.
Makes sense. Do the math first.
Always. Then you use a pipette again for accuracy to measure out exactly that calculated volume, V1, of the stock solution.
No guesswork. Definitely not for precise work. Transfer that measured stock solution into the correct size volumetric flask for your final volume, V2.
Okay.
And then, just like before, you add solvent up to the calibration mark on the neck, mix it well, and you've got your diluted solution.
Those two methods, from solid and dilution, sound like bread and butter lab skills.
Absolutely fundamental.
Okay, so we've got making solutions covered. We touch on like dissolves, like for whether something dissolves. But what about the limit? How much can you actually dissolve the solubility? Does anything else affect that max amount?
Oh, yes. Besides the nature of the solute and solvent, temperature and pressure are big players.
Pressure. I'm guessing that matters more for gases.
Huge difference for gases. For solids and liquids dissolving, pressure doesn't do much. But if you crank up the pressure of a gas above a liquid, much more of that gas will dissolve into the liquid.
Like in a soda bottle. High pressure keeps the CO2 dissolved.
Perfect example. Pop the top, pressure drops, gas comes out of solution, fizz.
And there's a law for that too.
Yep. Henry's law basically says the concentration of dissolved gas, C, is directly proportional to the partial pressure, P, of that gas above the liquid. C equals Kp, where K is a constant.
Got it. Pressure for gases. What about temperature? How does that affect solubility?
It's a bit mixed. For most solids dissolving in water, increasing the temperature increases solubility. You can dissolve more sugar in hot tea than in iced tea.
That seems intuitive.
Usually, but not always. Some solids actually get less soluble when you heat them up. It's weird but true. You really need to check a solubility chart sometimes.
Huh. Okay. What about gases in water?
For gases, the trend is much more consistent. Solubility almost always decreases as temperature increases.
So warm water holds less dissolved gas than cold water.
Exactly. That's why thermal pollution in rivers can be bad for fish, less dissolved oxygen, and why boiling water drives off dissolved air.
Okay, so temperature effects depend on whether it's solid or gas. Structure, pressure, temperature, factors controlling solubility. Now, the sources introduced this really cool idea, properties that don't care what the solute is, only how much is dissolved.
Ah, yes. Colligative properties. They are fascinating. The key idea, as the source says, is they depend only on the number of solute particles relative to the solvent particles. Not their size, not their charge, not their chemical identity, just how many there are.
That is wild. Just the count matters. For what properties?
Compared to the pure solvent, a solution will always have a lower vapor pressure, a higher boiling point, a lower freezing point, and it can generate osmotic pressure. Those four.
Lower vapor pressure, higher boiling point, lower freezing point, osmosis. Okay, let's unpack the first three. Why does adding solute mess with those?
It starts with vapor pressure. Imagine the surface of the liquid. Solvent molecules need to escape from there to become vapor. If you dissolve something non-volatile, something that doesn't easily become vapor itself, those solute particles basically block some of the surface spots.
Fewer spots for solvent molecules to escape from.
Exactly. So fewer solvent molecules escape into the gas phase, which means the pressure of that vapor above the liquid is lower. That's vapor pressure lowering. Raoult's law puts numbers on it, relating it to how much solvent versus solute you have.
Okay, lower vapor pressure. How does that lead to the boiling and freezing point changes?
Well, boiling happens when the vapor pressure equals the surrounding atmospheric pressure. If the solution's vapor pressure is lower at any given temperature, you have to heat it hotter to make its vapor pressure reach atmospheric pressure.
So it boils at a higher temperature. Boiling point elevation. Makes sense.
Yeah.
And freezing.
Freezing is about molecules getting into an orderly crystal structure. Solute particles kind of get in the way, disrupting that process. It takes a lower temperature to force the solvent molecules into that solid structure when there's solute around.
Freezing point depression. So you need to cool it down more to make it freeze.
Precisely. And both the boiling point elevation, ΔD, and the freezing point depression, ΔTVF, are directly proportional to the molality of the solution, that concentration unit based on moles per kilogram of solvent.
Right. The formulas were AT cams MK is some constant.
Exactly. KB for boiling, KF for freezing. There are specific constants for each solvent. They tell you how much the boiling or freezing point changes per unit of molality. The sources give water's values. KF is 1.86 degrees C per mol. KB is about 0.512. Really useful numbers.
Okay. And the fourth one was osmosis. Sounds biological.
It's huge in biology, but it's a physical process. It involves a semi-permeable membrane. Think of it like a very fine sieve. It lets small solvent molecules like water pass through, but blocks larger solute molecules like sugar or proteins.
Okay, a selective barrier.
Right. And osmosis is the net movement of the solvent across that membrane from the side with lower solute concentration to the side with higher solute concentration.
So the water moves to try and dilute the more concentrated side.
That's a great way to put it. It's trying to even things out. The sources mention things like red blood cells behaving differently depending on the solution they're in. That's osmosis in action.
And osmotic pressure.
That's the pressure you'd have to apply to the more concentrated side to stop that net flow of solvent. To counteract osmosis, there's a formula for it too, looks a bit like the ideal gas law.
Pi equals moles over volume times R times T. So it depends on the concentration and temperature.
Exactly. Now, tying this back, remember we said colligative properties depend on the number of particles?
Yeah, the count is key.
This is super important when your solute is an electrolyte.
Like salts, because they break apart in water.
Precisely. Sodium chloride, NaCl, doesn't just float around as NaCl units, it splits into ions. So one unit of NaCl actually produces two separate particles in the solution.
Okay, so dissolving 1 mole of salt gives you effectively 2 moles of dissolved things messing with the properties.
You got it. Which means electrolytes have a much bigger impact on colligative properties than non-electrolytes, like sugar, at the same initial concentration. We use something called the Van Hoff factor, symbol I, to account for this.
The Van Hoff factor, I? What does it represent?
It's basically the number of ions that one formula unit of the solute breaks into when it dissolves. For NaCl, I is 2. For something like potassium sulfate, K2SO4, it breaks into 2 K plus ions and 1 SO42 ion.
So 3 ions total, I equals 3.
Expected to be 3, yes. The source gives Fe3PO42 as an example, 3 iron ions, 2 phosphate ions, I equals 5. For non-electrolytes that don't break up, I is just 1.
And you just multiply the regular colligative property effect by I. That explains why salt is so much better at melting ice on roads than sugar would be. Same amount of stuff, but the salt makes more particles.
Spot on. That I factor makes a big difference.
Wow. Okay, we have really covered some ground here. From the very basics what solutions are, the whole dissolves thing, through the nitty-gritty lab work of concentrations and how to actually make these solutions accurately.
Yeah, both from solids and by dilution.
Then digging into what controls solubility pressure for gases, temperature, and finally these amazing colligative properties where just the number of dissolved bits changes everything from boiling points to osmosis. especially with that Van Hoff factor for electrolytes.
It really shows how understanding solutions connects basic molecular interactions to bulk properties you can measure and use. It's foundational stuff.
Absolutely. Yeah. Which leads to a final thought for you listening. We mentioned using salt on roads because of freezing point depression. Thinking about that, and maybe osmosis too, where else might these colligative properties, these effects that depend only on the number of dissolved particles, be playing a hidden but important role? Maybe in technology, industry, or even inside our own bodies. Something you chew on.